Okay, so this is Missoula talking to the Grace School in Sri Lanka. So Missoula, Montana, talking to the Grace School in Sri Lanka, and up to this point we have covered the NRGY 101 curriculum, the NRGY 202 curriculum, and now we're going into the NRGY 243 curriculum. And I have with me Jesse. I believe this is Jesse on the right, and I believe this is Ramia. I hope I'm saying that correctly, on the left, and I think this is Amorthika in the middle. So, all right, I'm going to go ahead and get into the lesson. There are a few things that we need to cover here. So the first one is this watt versus watt hour quiz, and I'm showing you the answers, and I want to make sure everything is clear before we move on. So the first thing, and this is something that we always start with, so watts versus watt hours. So we go back to our equation. Energy equals power times time, and we know that this is going to be watts times hours equals watt hours. So in this case, this dot means multiplication, and the dash, watt hours, is actually a name of electricity. So this is energy equals power times time. Okay, so the other thing to think about is, as we move through time, we have different amounts of power coming in, and let's just say we have a system with 3 panels, and they're each 300 watts. 300 watts, 300 watts, 300 watts. And if they are going, let's just start in the morning. So if we have, let's have midnight here. This will be 6 a.m. This will be noon. This will be 18 o'clock, and then 1800 hours, and then again midnight, noon, or 1200 hours. So the power is, the maximum power we know is going to be at about 900 watts. Early in the morning, so in the night it'll be 0, 0, 0. It'll come up, maximize, come back down, and then go back to 0. So this curve is power, and all of this under here is energy. That's power and energy. So if we go back at each chunk, we can say how much energy is coming in. So this, each one of those little pieces is another little bit of energy. Okay, I can see you again. I know the connection's kind of bad, but what I'm doing now, I'm going over this quiz. I'm going over the watts versus watt hours quiz. So let me go back here. I will share my screen. So I'm sharing this right now. So I'm going over watt versus watt hour. And what we're also going over is the, I'm going to go over this quiz. Let me find the quiz here. Actually, I'm going to share my full screen. I think that should be easier. Full screen. Okay, so hopefully you can see this now. And so what we're doing again is just a quick review of energy and power. And we can, what I'm showing here is that, again, energy equals power times time. Power is rated in watts. Time is rated in hours. And so the watt hour is a unit of energy. Power is energy per unit time, and here's time. So if we go through our day, starting at midnight, through 6 o'clock, through noon, through 18 o'clock or 6 p.m. and back to midnight, we might have as much as 900 watts coming through a system that's comprised of 3 panels, each with 300 watts. So this is how much energy flows through the system. So again, another thing to note is that current, I, flows through the current, and we always have some voltage across the terminals. And we'll get more to that later. But what I'm showing is that all of the energy under the curve is the sum of the power times the time. Okay. So the point is that you're always billed in energy. So are you? Hopefully, I can see you, but it's very slow. So I'm gonna continue with the lecture, and then I'll send it to you. Okay. So the next part is that the question is the rate at which energy is generated or used is measured in watts, and that should be clear from here. So the watt is basically the slope of this curve. So the watt equals 1 joule per second. So the watt is the rate. It's the steepness of the curve. So this would be high power, and this would be low power. Okay, next one. We'll just skip that one. Okay, this is a good one. How much energy does a 120 volt, 100 watt light bulb consume if left on for 24 hours? So let's do that. So again, we have energy equals power times time. We have power equals 100 watts. We have time equals 24 hours. So the energy equals 2,400 watt hours equals 2.4 kilowatt hours. Okay, so I hope this is coming through. Let me just type something in quickly.
Please try yes or no. As yeah. Hello.
Hi.
Please try to as the audio. இதுல டைப் பண்ணுங்க. Hello, uncle. We can't hear you.
Okay. Can you hear me now? I'm talking
Yeah,
now.
no.
Yeah, okay. Yeah, I think what's happening is that your video is going in and out, and so I'm just going to record this entire video, and I will send you a link to it. So I'm going to just do my best to deliver the entire lecture, and it's going to be, I think, too hard for me to get feedback. So I'm recording everything right now from my screen. And as soon as I'm done, I will share that with you. Okay?
Okay.
Okay, so I'll do my best for another 20 minutes, and then I'll send you the link. So thank you for your attention. I'm doing my best.
Thank you, uncle.
Okay, very good. Okay, I'll continue. So I was in the middle of. I was in the
Hello?
middle. Yeah, I'm gonna continue. It's too hard for me. I think our audio is too bad, so I'll send you the link. Okay, so the next question is, how much energy does a 100-watt light bulb consume if left on for 24 hours? So what I'm showing again is energy equals power times time. So power is 100 watts, time is 24 hours. If we multiply 100 watts by 24 hours, we get 2,400 watt hours equals 2.4 kilowatt hours. So 2.4 kilowatt hours, because 1,000 watts equals 1 kilowatt, etc. Or 1,000 watt hours equals 1 kilowatt hour. Okay, same thing, the capacity of a battery. So a battery stores energy. So again, energy is measured in watt hours. Sometimes it's also measured in amp hours. And I'll talk more about that shortly. Again, energy is watt hours. And if you are running different equipment, they're going to be measured in power. How much power do they draw? So for example, I'm looking there at the fan behind you, and I think the fan, so the fan, blowing. So the power of the fan So again, the power equals the volts times the current. And I'm just going to take a guess here that the voltage is 110 volts. You'll have to tell me. And I'm going to guess that the current is maybe, I don't know, maybe 1 amp. So the power is going to equal about 110 watts. So you have electricity coming in, from the wall. And you have mechanical, so this is electrical energy coming in. And here you have mechanical coming out, and it's likely about 110 watts. And that answers this question. So a refrigerator, light, TV, table saw, hairdryer, or the fan, which is maybe a hairdryer, looks like everyone's hair is dry, would have a power of maybe 110 watts. Okay, so let's go on to the next quiz. Basics of electricity. Okay, so let me make this a little bit larger so you can see. Okay, 100 feet of wire, number 6 copper, from a PV array to an inverter has a total resistance of 1 ohm. It says the PV array has an operational current of 14.2 amps and an operational voltage of 310 volts DC. What is the voltage drop? Okay, so for that, here's what we want to do. Here is our panel, PV, and we have wire coming from it, and it is 100 feet long, and it's number 6 copper. So we have a voltage here, and we have a voltage over here at the inverter, V2, and the question is, what is V1 minus V2 equals what? So the voltage, the change in voltage, equals the current times the resistance. And let's see, we know the current and we know the resistance. So V equals IR. So in this case, the current is 14.2 amps. 14.2 amps. And the resistance is 0.1 ohms. So the voltage equals the second one, 1.42 volts. 1.42 volts. So that's a very good problem for you to know. Very important. Important. Voltage drop. Okay, what's next? This one. So a 120 volt, 100 watt light bulb draws how much current? Okay, so let's do that one. So here we have a light bulb. Light bulb, kind of an old one. And we know that it's 100 watts. And we know that it's 120 volts. So again, power equals voltage times current. And the question wants to know how much current. So we can rewrite this as current equals power divided by voltage equals 100 watts divided by 120 volts. And for that, we'll use our calculator. 100 divided by 120 equals 0.83. Let's make sure that's on the answers. Yeah, there we go. 0.83 amps. So there we go. That's another very good question. Very good question. So it's this guy down here. Okay, so we finished question 2. now we have battery capacity expressed in amp hours, and the question is, what is the capacity of a 700 amp hour 48 volt battery bank? All right, another very good question. I don't know, I think John did a very good job with these. So we have batteries. And I also want to thank Tim Chester. Tim did a great job setting these up. So here we have our battery. And we know that the voltage equals 48 volts. And we're also given the capacity. It has 700 amp hours. So the capacity is 700 amp hours. 700 amp hours. So the energy equals the voltage times the current times the time equals 48 volts. And then here we can just combine 700 because there we have current and there we have time. And so together we have 700 amp hours equals, and we'll go back to our calculator for that one, 48 times 700 equals 33,600. 33,600 volt amp hours. And from that, this is the best answer right here, 33.6 kilowatt hours. 33.6 kilowatt hours, because we know that 1 watt equals 1 volt times 1 amp. And we know that 1 kilowatt equals, well, there's a couple different ways to do it, but we could do 1 volt times 1,000 amps, or 1 kilowatt equals 1,000 volts times 1 amp. So those are different ways to think about it. So there's the energy capacity in one battery with a voltage, again, a voltage of 48 volts and a capacity of 700 amp hours. So again, we go right back to our power equation. Energy equals power times time. We know that power is volts times current times time gives us energy. Fantastic. Fantastic. Okay. Moving right along. Okay, a 120 volt is powering a 5 amp load from a 48 battery. Ignoring inverter inefficiencies, how many amps are being drawn from the battery? All right, so let's look at this one. Let's look at this one. Okay, so this problem was a little bit good. It looks like everybody's still with me. Good to see you there. Thank you. I've got the sound turned off, But here we go. Here we go. I'm going to go back to the drawing board. So we were asked to find. So a 120 volt inverter is powering a 5 amp load from a 48 battery. This one's a little bit more challenging, but I've drawn it up here. So we've got an inverter that takes DC current. So this is direct current from a battery, and the battery has a voltage of 48 volts. So the current comes through, comes to the inverter. The inverter sends it out as AC current. AC is coming out at 120 volts. And let's just say we have a refrigerator running at 5 amps. So the power in the fridge is volts times amps. So 120 times 5 is 600. So this is a 600 watt system. Now, if we want to know the current, over here, again, we just use our power equation. We know the current equals the power over the voltage, because power equals current times voltage, and we rearrange it. And now we have 600 watts divided by 48 volts equals 12.5 amps, which is right there. Okay. Moving right along. Okay, this one's easy. 120 volts times 5 amps, 600 watts. Too simple. 120 times 5, 600. All right. Next one. Timeline quiz. This one is is important. It's not critical, but it's at least good to know. So, when was the photovoltaic effect first demonstrated? And for this one, I'm going to go back out to my to Tim Chester's solutions. So here we go. Let's get these going. So what Tim has done, he's done a little bit of online research. I think this is also in the book. But which decade was the photoelectric effect first demonstrated? 1830s. This is Becquerel observing the photovoltaic effect via an electrode exposed to light. So like a lot of experiments, a lot of discoveries, it was probably an accident. He had his conductive solution, some photons came in, and oh my gosh, here's more voltage. Okay, which year is photovoltaic technology born? So at this point, this was more like a science experiment, but in 1954, they took it and turned it into technology. So think of this as science, and think of this down here as technology. So using science to enhance our lives. All right, which of the following were early users of solar technology? Setting boats on fire. So in this case, believe it or not, if you have a parabolic mirror, and I think I can just find this. Let me just go out and find this online. So I'm going to get a new tab here. Oh, that's not a good one. You never know. Oh, no, it's not solar. I think this was Galileo. Well, I'm not finding it that easily, but anyway, legend has it that long ago Galileo was able to use solar energy to focus light in order to in wartime, actually, believe it or not. It's amazing how much energy there is in the sun. Also for lighting torches with a mirror. And my video's on right now, so you're not seeing, but do a little research and you can find those too. So this is focusing light with a lens or set of mirrors. So that's how to think about that one. All right, choose all of the following that are included in the solar timeline. So solar-powered car. I'll take you out to this. I'll take you out to this. Solar-powered car. Here's NRGY technology. Missoula College. So you can see here's our own solar car. This is a car that my students built and we raced in Houston. So there's one example. So there's, let me go back to my answer key. So solar-powered car. Solar-powered airplane, yep, believe it or not, that works. Solar-powered Stirling engine is another one. And then a solar-powered orbital astronomical observatory. So these are all things that have been demonstrated with solar power. Okay, that is all the time I have for today. I have another meeting, but again, thank you. Thank you very much. I will send the video so you can make sure that you know all of the material. Okay, ladies, thank you. It's been very fun, and I'll check in with John, and I want to make sure that when you're doing these quizzes that every one of you can know all of the answers, so that when we come to Sri Lanka and you do the project, you know what watts are, watt hours, amps, volts, power, so we can have the conversation. But again, thanks a lot, and I will see you probably on Friday. Okay, thank you. Bye. Bye.